SwayamPrabha. Digital India. Educated India.
Pollution control at mill stage, lecture number 3. We will be looking at how and what are the measures that a mill takes for controlling the pollution. Waste sources, what are the causes of the waste that are needing to be checked? Cotton in each of the unit operations or processes performed during bleaching, dyeing and finishing, the liquid waste that is generated has peculiar characteristic. The processes are mainly performed in different ways, either it could be a batch wise or continuous using different machines like care, jigs. The average values of pH range and BOD, that is biochemical oxygen demand, total solids in ppm range on analysis of waste from various textile mill show fairly high values of these parameters, indicating high waste discharge. In the last 2 lectures, we did look at what is the textile wastewater and what are the characteristics which need to be addressed in order to make the environment safe and sustainable. Because this wastewater, if it is discharged untreated, then it is going to create a big havoc for not only human beings, but also for aquatic animals. And therefore, we need to be more responsible and to understand what are the waste sources and how do we remediate. I also mentioned in the previous 2 lectures that we cannot forego any chemical use, because each chemical's use is designed for a particular process. However, we can minimize the use and optimize the functionality. Controlling pollution at a mill stage, that means in a textile mill, what are the controlling factors that we need to see and to evaluate, because if we are not careful about these things, then the discharged water or the textile effluent is bound to be highly contaminated. So, we need to understand how pollution control can be done at mill stage. Controlling pollution at a mill stage involves implementing various measures to mitigate the environmental impact of industrial activities. Here are several strategies commonly employed. Waste management, implementing efficient waste management systems to reduce the amount of solid waste generated by the mill. This includes recycling, reusing materials and proper disposal of the hazardous waste, because this is a very important factor where waste management is of prime importance. All the amount of solid waste that is generated in the mill needs to be either recycled or reused, or it should be sent for landfilling, or if it is a hazardous waste, then the proper disposal should be done. Water conservation and treatment. Now, this is another secondary or I would say primary factor, where water, which is a very important commodity and it is becoming scarce every day, that there is a scarcity of water, fresh water. So, implementing water conservation measures to minimize water usage in mill processes is also equally important. Additionally, treating wastewater before discharge to ensure that it meets regulatory standards and does not contaminate local water sources. This is the prime important fact, that we cannot afford to contaminate the local water bodies by letting out these effluent into the water bodies. So, controlling pollution at mill would not only require pollution in the wastewater or the solid waste, but also air pollution control. Installing air pollution control devices such as scrubbers, filters, electrostatic precipitators to reduce emissions of particulate matter, volatile organic compounds, that is VOCs, and other pollutants released during milling operation. So, during the milling process, actually, seen or unseen, there are lot of particulate matters, there are lot of volatile organic compounds, VOCs, which we cannot see by our naked eyes, but they exist and they also need to be controlled, and therefore, installing a air pollution control device is a must. Efficiency of energy. Improving energy efficiency through use of energy efficient equipment and processes, as well as adopting renewable energy sources such as solar or wind power to reduce reliance on fossil fuels and decrease greenhouse gas emissions. Now, this is another responsibility, that we need to conserve energy, and we all know that fossil fuels are depleting, and by 2050 we will have to be totally dependent on renewable energy sources rather than the conventional energy sources of petroleum and coal. Therefore, we have to have energy efficiency by using energy efficient equipment and processes, such as adopting renewable energy sources through solar and wind power, and therefore, we will be then able to reduce our reliance on the fossil fuels. Environmental monitoring. Regular monitoring of air, water and soil quality in and around the mill to assess the impact of operations on the environment and identify areas of improvement, because environmental monitoring will render us, at least as responsible citizens, to know that we are not responsible for causing any air, water or soil contamination. Controlling pollution. Compliance with regulations. Ensuring compliance with environmental regulations and standards set by local authorities and regulatory agencies to minimize the environmental impact of mill operations and avoid penalties. Because now the environmental ministry and the pollution control board people have become very, very aware, and they are implementing these compliances and regulatory methods and standards, and they are forcing the mill people to practice them, so that they do not have to pay any penalties. Employees training and awareness, because after all, those who are working in the mill should be aware of these principles. If we say, okay, we need to conserve energy, if we say we need to conserve water, if we say we need to recycle the chemicals that are present in the effluent, but if the workers are not aware of this, then who takes care of this? So, therefore, employees' training and awareness is equally important. Providing training to employees on pollution control measures and raising awareness about the importance of environmental stewardship to encourage responsible behavior and compliance with environmental policies. Then only they will be able to practice it. Community engagement. Engaging with the local community to address concerns related to pollution and environmental impact, as well as seeking feedback and input on pollution control initiatives. By implementing these measures and continuously improving environmental management practices, mills can reduce their environmental footprint and contribute to sustainable development while fulfilling their operational requirements. So, if all the mills are taking proper measures, continuously they are practicing environmental management practices and reducing the environmental footprint by making it more sustainable, then it is a very ideal situation, and that is how every mill should implement these practices. Measures to be taken for pollution control. So, therefore, there are measures, and if a mill owner is following those strategies, then there is no way that he or she will be penalized for creating any environmental issues. Pollution control in mill is crucial for mitigating the environmental impact of industrial operations. Here are some specific measures that can be taken. Now, there are certain set rules for this. Either you follow every of them or you follow some of them, at least you have to follow some of them. Invest in clean technologies. Upgrade equipment and machinery with modern environmentally friendly technology that reduces emission and pollutants. This includes investing in energy efficient machinery, low emission boilers and advanced filtration system. So, either of these they can invest in. They can invest in energy efficiency machinery, or they can have low emission boilers, or they can use advanced filtration system. Implement best practices for waste management. Develop comprehensive waste management plans that prioritize reduction, reuse and recycling of waste material generated during milling operation. So, that means they should follow the 3 R's: reduce, reuse and recycle of the waste material. Properly handle and dispose of hazardous materials according to regulatory standards. And whatever are the hazardous materials like heavy metal, solid waste, these which have been precipitated, which cannot be recycled or reused, then they should be properly disposed, and this is a very standard practice. Measures to be taken for pollution control. Install pollution control devices. Install and maintain pollution control devices such as scrubbers, electrostatic precipitators and bag houses to capture and remove particulate matter, volatile organic compounds, that is VOCs, and other harmful emissions from air and water streams. So, when we go around a mill, we see a lot of air pollution, and some of them we cannot even perceive through our eyes, but they exist. So, they need to be captured and removed, and this can only be done if pollution control devices are installed. Optimize water usage and treatment. Implement water conservation measures to minimize water consumption in milling process. In the very beginning of the first lecture, I had mentioned that textile processing, wet processing alone requires huge amount of fresh water. So, if we try to object our processing into using lesser amount of water in an optimized manner and also treat that whatever water we have used, that should be the most ideal situation. Treat wastewater before discharge to remove pollutants and ensure compliance with regulatory standards. And this way we can implement water conservation measures to minimize water consumption in the milling process. Implement closed loop water system wherever possible to reduce water usage and wastewater generation. And we saw that this closed loop water system, where the squeezing water is again reused in the process, or the dye bath, the new dye bath is enhanced with the recovered water, dyed water. So, those kind of practices are very good. Monitor and improve air quality. Regularly monitor air quality within and around the mill premises to identify sources of air pollution and implement measures to reduce emissions. Conduct regular maintenance of equipment to prevent leaks and malfunctions that could contribute to air pollution. So, in every way there should be an exercise to monitor and to keep the air quality good in an improved manner. How the regular monitoring of the air quality can help to do that. More types of measures that need to be taken. Promote energy efficiency. Improve energy efficiency by optimizing processes, upgrading equipment and implementing energy management systems. Switch to renewable energy sources such as solar or wind power to reduce reliance on fossil fuels and lower greenhouse gas emissions. So, one has to keep in mind that we need to promote energy efficient processes, and renewable energy such as solar or wind energy in place of fossil fuel usage can definitely reduce the greenhouse gas emissions. Less of carbon dioxide will be emitted. Employees training and awareness, and I just told a while ago that we cannot do these practices without training the people who are working in that mill. So, it is very important for training the employees and to make them aware. Only then they will practice what is being asked to them to practice. Provide comprehensive training to employees on pollution control measures, safe handling of chemicals and proper waste management practices. Foster a culture of environmental responsibility and encourage employees to actively participate in pollution prevention efforts. Compliance with regulation. Stay informed about environmental regulations and standards relevant to mill operations and ensure full compliance with all applicable laws. Regularly conduct audits and inspection to assess compliance and address any non-compliance issues promptly. So, if the mill owner is taking care of all the regulations and is taking care of the compliance of the regulation and the standards, then it is a very good situation for the mill owner as well as for the environmental sustainability. Continuous improvement is needed. Engage with stakeholders, foster positive relationship with local communities, government agencies, environmental organizations and other stakeholders. Seek feedback and put on pollution control initiatives and actively address concern raised by the community. Now, it is just not possible to work in isolation. So, stakeholders also need to be engaged, and in order to do that, there is a requirement to have a positive relationship with the local communities, with government agencies, with environmental organization. If all three of them work in synchronization, then only all this implementation and compliance can take place. Continuous improvement. Establish a system for ongoing monitoring, evaluation and continuous improvement of pollution control measures. Regular review environmental performance data, identify areas for improvement and implement corrective actions as needed to minimize environmental impact and enhance sustainability. See, it is not a one-time process. It is a continuous process which needs to be practiced all the time, and all this regular environmental performance data should be kept updating, and then identify areas which require improvement or take corrective measures where some slag has taken place in order to minimize the environmental impact and to enhance sustainability. By implementing these measures, mills can effectively control pollution and minimize their environmental footprint while maintaining efficient and profitable operations. Now, when we look at this chart, we see that pollution effect of just the cotton processing waste is of this order. How much of waste, gallons of waste that are generated only in slashing and sizing, where the pH is 7 to 9.5, the BOD goes ranges from 620 to 2500. Then desizing creates so much of rise in BOD, that is biochemical oxygen demand. It goes to 17,000 to 52,000, and slowly the waste is also increasing. It is rising from 940 to 1100. Then by curing, by scouring, by bleaching, it continuously enhances the waste that is generated, and all this is adding up. If we are doing a dyeing process, by just using aniline black, the waste that is generated is of the order of 15,000 to 23,000. But if we use direct dyes or even indigo dye, the waste is minimal, which is of the order of 600 to 6,000 or 1700 to 6400. So, you just see that different processes keep on adding the waste that is generated, and the pH also keeps fluctuating, and so does the BOD. But you may have noticed that the maximum contributor of BOD is the desizing, and therefore that is, but we cannot omit this desizing process, hence we need to only make a control at the mill stage. If we look at the waste that is generated from synthetic fiber in a finishing mill, we will see that rayon process, on an average is generating total solid of 5500, whereas if salt takeoff has taken place, waterproofing, scouring and dyeing, there are different amounts that are used. If acetate processing is done, then there are other estimated total solid range that are generated. So, all the processes contribute. If we look at the nylon processing, we will see scouring, first rinse itself will create so much of BOD. Then second rinsing is less, dyeing is still less. So, we see that the crucial step in nylon processing is the first scouring step, and that creates the maximum total solid range and also the maximum of BOD. Therefore, we understand that whether it is synthetic fiber or cotton fiber, they have their own ranges of total solid creation and BOD creation, increase in BOD. If we look at the total pollution potential of various textile mill solution, and we say that okay, one single process, only the experiment desizing solution, first rinse follows, you see that the BOD is of 2600 range, but caustic here, that is the first boil and the second boil put together, can go up to 1400. So, that is the ppm level we are talking about, and even the bleaching processes can be very high. So, what I mean to tell you by giving these charts, by showing these charts, that these are very intensive in terms of increasing the BOD or the total solids, and therefore, we need to then look at it from the remediation point of view very carefully. Now, when we look at waste sources in wool, wool needs grease scouring to remove all the natural and acquired impurities from wool fiber. Pollution potential of various individual processes compare well with that of the combination of various processes. Grease scouring and wash after fulling are of two main sources of pollution. Thus, can be generalized that wool wastewater discharges would generate more than 50% from scouring and the rest from the other chemical processes. So, what it means that it is not that uniformly all the processes contribute equally. Some processes, as what we saw in the case of cotton, synthetic material as well as wool, that one of the process contributes to maximum pollution, others may be small contributors, but in totality when you look at the textile effluent which comes out at the end of the finishing step, is the one which we have in hand, which we need to handle, which we need to remediate. So, waste in wool processing. Wool processing involves several stages, each of which generate various types of waste. Here are some common sources of waste in wool processing. Shearing waste. Shearing is the process of removing wool from sheep. This process generates wool clippings or wool grease containing lanolin, dirt and other contaminants. While lanolin has some commercial uses such as cosmetics and pharmaceuticals, the bulk of shearing waste is typically considered as a byproduct. So, not all waste can be recycled or reused, some are just an utter waste. However, lanolin is usable. Similarly, scouring waste. After shearing, wool typically undergoes scouring, a process to remove grease, dirt and impurities. Scouring generates wastewater containing lanolin, dirt and residual chemicals from the scouring agents. This wastewater, if not treated properly, can have significant environmental impact. So, therefore, it is extremely important that these are treated before they are rendered into the water bodies. Waste in wool processing could also arise from sorting and grading waste. Wool fibers need to be sorted and graded based on factors like fiber strength, fiber length, fineness and color. This process generates waste in the form of shorter or coarser fibers as well as contaminated or discolored wool. So, there are two different types and they need to be graded or sorted out. Carding and combing waste. Carding and combing are processes used to align fiber, wool fiber and remove impurities. Waste from these processes include shorter fiber noils, that is short fibers removed during combing, and waste generated during cleaning and maintenance of carding and combing equipment. So, this also, because fibers are of different length, and if they are of different length, then they need to be sorted, and carding and combing also straightens the wool fiber. Spinning waste. Spinning wool into yarn can result in waste including broken or tangled fibers, spinning machine waste and waste from yarn quality testing. So, there are several types of waste that are generated and all need to be, because they accumulate. So, if they accumulate, this is a solid waste. Now, this solid waste has to be properly disposed or recycled, or some important ingredient can be extracted, like lanolin could be extracted from the wool and that could be reused. Dyeing and finishing waste. Dyeing wool involves the use of dye stuffs, chemicals and auxiliary agents. Waste generated during dyeing includes excess dye, chemicals and wastewater containing dye residues and contaminants. Similarly, finishing processes may generate waste in the form of sludge or residues from treatments such as sizing, bleaching or softening. So, when we look at the waste generated from wool processing, it is a whole lot of waste that is generated. Garment production also creates waste. In the production of wool garments, waste is generated during cutting, sewing and assembly processing. This waste include fiber scraps, trimmings and offcuts. Packaging waste. Packaging material used for shipping wool products such as cardboard boxes, plastic wraps and packaging inserts contribute to solid waste generation. So, there are solid waste that are generated from various angles in the wool processing and all need to be addressed. So, strategies to managing waste in wool processing. How do we now manage all these different types of waste? Source reduction. Minimizing waste generation at source through process optimization, efficiency improvement and product design changes. Recycling and reuse. Identifying opportunities to recycle and reuse waste materials within the facility or in other industries. So, first thing is how to minimize at source, that less generation of waste is created through an optimized process. And if possible, recycling and reuse of some of the waste, if it is possible, should be done either for its own facility or for any other industry. Treatment and disposal. Proper treatment and disposal of solid and liquid waste to prevent environmental contamination. Now, this is very important because we need to properly treat the waste. We cannot dump it anywhere. If it is a solid, should be properly disposed. If it is a liquid, it should be properly disposed in landslides and places where landfills are done, and therefore, it will not contaminate the environment. Compliance with regulation. Ensuring compliance with environmental regulations and standards related to waste management in wool processing should be implemented strictly. Implementing sustainable practices and technologies can help reduce the environmental impact of waste from wool processing, while also improving resource efficiency and operational performance. Waste and chemical recovery and reuse. Biologically or chemically treated water may be suitable for reuse in processing as well as cooling tower makeup. Reuse would result in reduced water consumption and wastewater volume. So, if we believe in the 3 R's, reduce, recycle and reuse, then definitely it is a win-win situation. In cotton processing, about 15% of the processed water can be reused. Recovery of glucose as desizing waste could be affected by evaporation. The recovery of chemicals such as caustic soda from mercerization is by heating the caustic soda liquor. The concentrate, when evaporated, 90% of caustic soda can be recovered. So, in cotton processing alone, there are at different stages they can be recovered. They need not be mixed with the entire textile effluent. Once they are mixed in the entire textile effluent, then the recovery becomes more tedious. In wool, use of continuous countercurrent processing can significantly reduce water consumption. Linolene may be recovered via solvent extraction. So, there are ways of recovery and reuse. Recycling of textile waste. Recycling and reuse of textile waste has assumed importance in the recent past in our country, and not only our country, globally. With the rise in living standards, the demands for textile and clothing is expected to grow. Like any other industry, this industry also generates all categories of industrial waste, namely liquid, solid and gases. Various useful materials can be recovered from these wastes by utilization of new processes. The wastage of raw material can be reduced by improving manufacturing processes at every stage, thereby saving in the major inputs. So, a whole lot of strategic plan has to be made about the recycling of the textile waste. During the process, certain kind of waste such as solid waste can be recovered by adopting new technologies, whereby these wastes can be converted into useful materials for other application. Waste utilization. Textile industry is one of the largest industries which consumes energy in the form of heat. New technologies are required to recover some percentage of the loss of energy. So, The aim in today's time is that how do we recover some percentage of the energy loss. So, waste utilization of the textile industry is gaining vital importance in the Indian textile industry, as international legislation are also to come up into force in our country. The country is looking for export market, and hence certain standards laid down by the European countries have to be adopted. Now, let us understand about the solid waste. Basically, there are two categories of solid waste. One from the manufacturing waste, which is the waste from the various manufacturing processes, and the second one is recovered and reclaimed waste, which is waste collected after use and then reprocessed. The fabric waste from carding, combing, drawing, spinning are all soft waste. Waste produced after spinning and twisting and the process of weaving and knitting is called hard waste. Finishing waste are also called locks, which are from the finishing process of the fabric. Reclaimed wastes are mostly in the form of rags and old discarded clothing. There are wool waste and non-wool waste. So, all kinds of waste are possibly there. Now, we need to see where we can process what and reuse it. Solid waste generated in textile processing. So, textile processing, both synthetic and natural, generate various types of solid waste throughout its different stages. These waste materials can have significant environmental impact if not managed properly. Here are some of the common sources of solid waste in textile processing. Fibers, fiber processing waste. During the production of synthetic fibers, there may be waste generation in the form of polymer residues, trimmings and offcuts. These materials may include unreacted chemicals, byproduct of polymerization or imperfectly formed fibers. So, there could be many ways by which fiber processing waste could be generated. Similarly, there are yarn and fabric production waste. Trimming, scraps and defective yarns or fabrics are common waste products in the manufacturing of textiles. These can accumulate during processes such as spinning, weaving and knitting. Dyeing and finishing waste. Dyeing processes generate wastewater containing excess dye, chemicals and additives. Solid waste can also arise from dye baths such as sludge or sediment from filtration and treatment processes. Similarly, finishing treatments may produce solid residues or sludges containing chemicals or additives. So, there are various sources. Even during the dyeing and finishing processes, there are waste generated from the sludge or solid waste which are which require treatment. Packaging waste we have already spoken earlier. Packaging materials such as shipping textile would require cardboard boxes, plastic wraps and packaging inserts contribute to solid waste generation. Garment production waste. In the production of garments, cutting processes generate scraps and offcuts of fabric, which contribute to solid waste. Additionally, packaging materials for finished garments such as hang tags, labels and plastic bags can become a waste. So, garment production also creates lot of waste. It is not that it is only the chemical processing that is creating the waste. Maintenance and cleaning the waste. Maintenance activity in the textile processing facility may produce solid waste such as used in equipment parts, lubricants and cleaning agents, because even the machineries create some sort of waste which can be eventually adding to the solid waste. Managing the solid waste from the textile processing typically involves several strategies: source reduction, as we talked in the very beginning, minimizing waste generation at the source, process optimization, efficiency improvement and product design changes. So, if we look at minimizing at the source, that is the best, that less waste will be generated. Recycling and reuse is the second best. If we can identify opportunities to recycle or reuse waste material within the facility or for any other industry, then that is one of the most ideal situation. For example, textile scraps can be recycled into new fibers and used as insulation material. Treatment and disposal. Now, this is the most important part, that whatever waste we have generated, are we able to totally treat them or dispose them properly. Proper treatment and disposal of solid waste to prevent environmental contamination is very important. This may involve incineration, landfilling or composting, depending on the nature of the waste and local regulations. Waste to energy. Some textile waste, particularly organic materials, can be converted into energy through processes such as anaerobic digestion or thermal conversion. So, how do we get from waste, can we generate energy? And that is possible, because there are processes developed like anaerobic digestion or thermal conversion. These can be utilized. Compliance with regulation. Ensuring compliance with environmental regulation and standard related to solid waste management in textile processing. In cotton textile mill itself, waste is generated from different processes. An integrated cotton textile mill produces its own yarn from the raw cotton. Production of yarn from raw cotton includes steps like opening and cleaning, picking, carding, drawing, spinning, winding and warping. All these sequences are dry operations, as such do not contribute to liquid waste in the mill. Carding, it is a process in the manufacture of spun yarn, thereby the staple is opened, cleaned, aligned and formed into continuous untwisted strand called sliver. Drawing, it is the process of increasing the length per unit weight of the sliver. Combing, a process or a method to remove short fibers, foreign matters from cotton stalk by pressing it through a series of needles or comb. Spinning, it is a process by which a long strand of fiber is drawn out to a short strand and converted into a yarn. After drawing out, it is subjected to twisting and resulting yarn is wound into a bobbin. So, there are many methods. They may not be contributing to liquid waste, but they are contributing to solid waste in cotton mill. Then comes winding. It is a process of transfer of the yarn or thread into one type of the package to another. And then comes weaving. It is a process of interlocking two yarns of similar materials so that they cross each other at right angles to produce a woven fabric. The entire liquid waste from the textile mill comes from the following operation of slashing or sizing, scouring, desizing, bleaching, mercerizing, dyeing and finishing. In slashing, to give it a tensile strength and smoothness, necessary float is subsequently then woven. The yarn is strengthened by loading it with starch or other sizing substance. Waste originates from this section due to spills and the floor washing at the weekend. After slashing, the yarn goes to weaving. The prepared cloth now requires scouring and desizing to remove natural impurities and the slashing compounds. So, a lot of chemicals are generated during these processes of slashing, scouring, desizing, bleaching, mercerizing, dyeing and finishing, and that is the main source of contamination in liquid waste. So, wastewater treatment need to be done, and in order to do a cheap wastewater treatment, one can use activated carbon. Treatment with activated carbon use for the treatment of textile finishing or dye house effluent is possible where one or more of the following condition exists. Raw water and or effluent treatment costs are very high and or makeup water treatments are overloaded. So, if you have either of these two conditions, whether the raw water is very high in contaminants, or if the water system treatment system is overloaded, then simply by adding activated charcoal one can achieve. An ideal example in carpet mill, where use of activated carbon adsorption to treat and then recycle 80% of wastewater is possible. As no biological sludge is formed, solid waste disposal is minimized. So, there are methods of wastewater treatment. However, that is not the case in synthetic fabric processing, because the waste that is generated from synthetic fabric processing is estimated and can be reused up to 10% of its wastewater through recovery. Recovery of zinc from viscose rayon processing by ion exchange precipitation and flotation method is practiced in many places. Waste from the manufacture of the synthetic fiber resembles chemical manufacturing waste and depends entirely on the raw material used and the process adopted. So, when we look at these processes, whether it is a synthetic fiber or a cotton natural fiber, they have their own strategies for recovery. They are not common to both. Waste from synthetic fabric processing. The most prominent man-made synthetic fiber are rayon, nylon and polyester. These fabrics require no processing for the removal of natural impurities as they are man-made. Manufacture of synthetic fabric involves two steps: manufacture of the synthetic fiber and preparation of the cloth. These two steps may be carried out either in one integrated plant or may be separated in two different plants. A typical synthetic fiber nylon 6 is obtained through polymerization of caprolactam and subsequently pelletization takes place, drying, remelting in extruder, spinning and twisting. So, here it is completely different type of synthetic fabric processing. It is not the same as what we saw in the case of cotton or wool. Synthetic textile processing. The waste from the manufacture are usually characterized by a colloidal type turbidity, a typical color, a low alkalinity, that is pH around 7.5, high amount of total solids of the order of 2500 milligram, and comparatively small amounts of suspended solids. The waste usually contains a large amount of nitrogen entirely of organic origin. The waste is also characterized by high COD value in the order of 500 milligram per liter, though the BOD is found to be very low, around 50 milligram per liter. So, you see that if we compare synthetic fiber with natural fiber, these parameters are quite different, that is the COD, the BOD and the total solid content. So, synthetic textile fiber actually involves conversion of synthetic fibers into various textile products through a series of mechanical, chemical and sometimes biological processes. Synthetic fibers are derived from petrochemicals and other synthetic materials as opposed to the natural fibers like cotton or wool. An overview of the synthetic textile fiber steps, that is fiber production. Synthetic fibers such as polyester, nylon, acrylic and polypropylene are manufactured through processes like polymerization, spinning and drawing. These processes produce continuous filament or staple fibers depending on the intended use. Texturing and crimping. To enhance the texture and bulkiness of the synthetic fibers, they may undergo processes like texturing and crimping. This can improve the feel and appearance of the final fabric. Synthetic textile processes require yarn formation. So, synthetic fibers are spun into yarns using various techniques such as ring opening or open end spinning or air jet spinning. Yarns may be single or plied depending on the desired characteristic of the final fabric. Weaving or knitting. Yarns are woven or knitted in fabric structures on looms or knitting machines. Weaving produces woven fabric while knitting produces knitted fabric. Different weave or knit structures and patterns can be achieved to create different fabric patterns and properties. Dyeing and printing. Synthetic fabrics may undergo dyeing and printing processes to add color and pattern. Dyeing can be done at the fiber, yarn or fabric stage using various dyeing techniques such as batch dyeing, continuous dyeing or digital printing. Synthetic textile printing then also requires finishing, and so finishing is done, then quality control and testing is also required. Finishing is done by the same processes of heat setting, calendaring, coating, laminating or adding finishes for water repellency, flame retardancy and antimicrobial properties. And then of course, the cutting and the sewing and the packaging and distribution takes place in a similar manner as what other cotton or wool products are done. In conclusion, we can say pollution control at the mill stage of textile processing is essential to mitigate environmental impact of textile manufacturing. Wastewater treatment is very essential. One of the primary concern of textile mill is the generation of wastewater containing various pollutants such as dyes, chemicals and organic matter. Implementing effective water treatment processes such as biological treatment, chemical coagulation and advanced oxidation helps to remove or neutralize the contaminants before discharge. Similarly, effluent monitoring is equally important. Regular monitoring of effluent quality is crucial to ensure the compliances with environmental regulation and standards. Monitoring the pH, COD, BOD, TSS is also very important. In conclusion, pollution control at mill stage of textile processing is critical for minimizing the environmental impact of textile manufacturing. By implementing effective wastewater treatment, optimizing resource efficiency, managing solid waste, controlling air emissions, ensuring compliance and fostering innovation, textile mills can reduce pollution and move forward for more sustainable practices. Thank you.